Hey, welcome to the Electronics channel. In this video, I'm going to do a brief overview of doing arithmetic with significant figures. And we'll start with multiplication and division. And with multiplication and division, the number of significant figures in the output matches the number of significant figures of the number in the input that has the least number of significant figures. And that's a jumbled sentence, but I'll do a couple of examples that will hopefully help you see what I mean. So the first example, we'll look at a couple of numbers, and these are just arbitrary numbers. They don't have any particular units or meaning. 5.41 times 0.93. So in this multiplication, the 5.41 has 3 sig figs, and 0.93 has 2 sig figs. 0.93 has less significant figures, so the answer is going to match that number of significant figures. The answer needs to have 2 sig figs. The answer, when I multiply it all out, if I was to punch this into my calculator, it's going to give me a value of 5.0313. But since we're only going to 2 sig figs, the actual value that we can use is 5.0. It's the exact same thing with division. So if I have a number 1001.0 and I divide that by 6.31, 1001.0 has 5 sig figs and 6.31 has 3 sig figs. So that means my answer is going to also have to have 3 significant figures. If I plug the number into the calculator, I'll get something 158.6 something, I believe. But since I could only have 3 significant figures, the value I can use is 159. So there's one caveat that I should mention, and that's when you're dealing with a counting number. So let's say I have 2 blocks, and they each weigh 1.001 kilograms. And I want to know what the mass of the 2 of those blocks is. I mean, I could add them together, but if we're looking at multiplication right now. So when I'm multiplying 1.001 kilograms by 2, because I've got 2 of these blocks, I can assume that counting number has an infinite number of significant figures. So the value in that multiplication of 1.001 kilograms times 2, 1.001 is the value that has the least number of significant figures, because this whole number, this counting number, has an infinite number. So there's 4 sig figs there. When I do that multiplication, I get 2.002 kilograms, and that answer also has 4 significant digits. Now with addition and subtraction, the way that you figure out the significant figures of the output is the value of the input that has the coarsest resolution is the value that determines the resolution of the output. So I'll give you an example. Let's say we have a couple of numbers here that we're adding together. We have the number 10 plus 0.39. So the resolution of this number is to the nearest ones, whereas the resolution of this number is to the nearest hundredths. So the answer needs to use the resolution of the coarsest value, the coarsest input, and so the ones would be that coarsest input. If we plug this into a calculator, we would get the number 10.39. But of course, we have to keep it to the same resolution as this input with the coarsest resolution. So that'll just be equal to 10. With 2 significant figures. Similarly with subtraction, if we have 54.395 and we subtract the value 4.4, this number has a resolution to the thousandths, whereas this has a resolution to the tenths. So this value here defines what our resolution for the output is going to be. if we plug this into the calculator, we get the value 49.995. But since we can only go to the resolution of tenths, this is going to be equal to 50.0. With addition and subtraction, there's also a caveat, and that's when you're dealing with units that are on different scales. So if I have two, let's say I have two masses, one is 50 kilograms, and the other is 30 grams. So it looks like they both have the same resolution, but of course we need to look at what those numbers are actually representing. So if we converted both of these into kilograms, because they're not both in the same units. Well, 50 kilograms, that's still 50 kilograms, but 30 grams is 0.030 kilograms. So if we had both of these masses and we were to add them together, we would have 50 kilograms plus 0.03 kilograms. But remember, we're looking at the input that has the coarsest resolution, so this is to the nearest ones. So the answer here, we can only go to the nearest ones. If we plug this into our calculator, we'd get 50.03 kilograms, but our resolution only allows us to go to the resolution of that digit, the ones column. So we have to round it to 50 kilograms. So one more caveat or word of warning, and that comes when you're doing sequential calculations. So if you're doing a sequence of multiple calculations and trying to keep your significant figures throughout those calculations, if you were to round to your proper significant figures in every step, it's possible and even likely that you're going to end up with a rounding error. So it's good to keep 2 or 3 digits past the significant figure when you're doing your calculations, or even all of them if you're doing your calculations on a calculator. To see how a sequence of calculations can get messed up if you are keeping your sig figs all along the way, let's take a look at a fairly simple example here. And let's say that we have that 5 kilogram mass and that 3 kilogram mass. And let's say we put them together and we put them on the end of a lever arm. So we put the big one and the little one together on this lever arm, and let's say that lever arm is 2 meters long, and we want to figure out what's the torque on that lever arm when that mass is put there. So if we're carrying our significant figures the whole way, when we have a 5.0 kilogram and a 0.03 kilogram object together, well, because of the rounding and keeping our sig figs, the total mass is 5.0 kilograms. Now that total mass, the force that mass is exerting on the lever arm is equal to the mass times the gravitational constant, not the gravitational constant, the acceleration due to gravity at the surface of the Earth. We multiply those two numbers together and we get 49.05 newtons. But we need to round, remember, so that we're going to be keeping two significant figures. So it's really 49 newtons. And the torque that's going to exert is going to be the 49 newtons times the length of the lever arm. And we get 98 Newton meters. Okay, that was carrying our sig figs throughout the whole calculation. Now if we don't do it through the whole calculation, we have a 5 kilogram mass and a 0.03 kilogram mass. So the total mass of that object is 5.03 kilograms. The force that mass is exerting on that lever arm will be the 5.03 kilograms times 9.81 meters per second squared. And that gives us a value of 49.344 newtons. And then the torque will be the force times the length of the arm, so 49.344 newtons times 2.0 meters. That gives me 98.688 Newton meters. That's to 3 decimal places. But if I work backwards, or I want to match the number of significant figures that I have in my calculation where I carried the sig figs through the whole thing, see I have 2 sig figs, but if I'm rounding this number, I will round up to 99 Newton meters. So I get different answers between these two because I rounded as I was going through, and I carried extra digits as I was going through this calculation. Oh, that's it. See? No more. That page is blank. I went through this page already. All right, I hope you learned a little bit about sig figs and doing calculations with them. Thanks so much for watching. I will see you in the next video.